All right, buckle up, because we're about to dive into one of the most thrilling intellectual showdowns in modern thought, the epic battle between scientific realism and anti-realism. This isn't your typical academic squabble over some obscure detail in physics or biology. Oh no, this is much bigger. This is a debate about the very soul of science, about what it's trying to achieve, and what we, as curious humans, can hope to get out of it. In a way, it's the ultimate of asking, what's the point of science? What are we really doing when we do science? Think about it. We all have some idea of what science is up to, right? We learn about it in school. We see it on the news. We benefit from its technological offspring every single day. But here's where things get interesting, where the plot thickens, and where the philosophical sparks start to fly. On one side of the ring, we have the Save the Phenomena crew, the scientific anti-realists. They're like the pragmatists of the science world, the no-nonsense, just the facts, type. They say, look, science is about making accurate predictions, building useful models, and giving us a handle on the stuff we can observe and experiment on. It's about making sense of the data, describing what's happening, and creating theories that accurately reflect our experimental results. As long as a theory predicts well and is consistent with our observations, it's doing its job. It doesn't matter if our models don't perfectly reflect reality as long as they allow us to make predictions about the world and build cool gadgets. It's a bit like saying a map doesn't need to be a perfect, scaled-down replica of the terrain as long as it gets you where you need to go. It's a good map. Who cares if it doesn't show every single blade of grass or every tiny pebble? But then, in the other corner, we have the truth seekers, the scientific realists, the ones who yearn for something more. They're the ones who say, hold on a minute. Science isn't just about making predictions, it's about uncovering the truth about reality, even the parts we can't see directly. They believe that science should strive to tell us the real story of what's going on, the why behind the what, the hidden mechanisms that make the universe tick. And often, that means venturing into the realm of the unseen, talking about things like tiny neutrinos, invisible protons, or the intricate double helix of DNA, stuff that's way beyond what our naked eyes can perceive. These aren't just convenient fictions or theoretical tools. They argue they're real things, as real as the chair you're sitting on, even if they're too small or too elusive to be seen without specialized instruments. So, which side are you on? Are you a save the phenomena kind of person, content with accurate predictions and useful models? Or are you a die-hard truth seeker, yearning to know the deep, underlying reality of the universe, even if it means relying on theories about things we can never directly observe? This is the question that has put scientists and philosophers at each other's intellectual throats for centuries. It's a question that's been debated in smoky backrooms, in prestigious lecture halls, and in countless academic papers. And believe me, the arguments are fascinating, the counterarguments are mind-bending, and the stakes are higher than you might think. Now, you might be thinking, this all sounds a bit armchair philosophy, right? Who cares what the aims of science are, in some abstract sense? Scientists just do science. They don't sit around pondering these lofty questions. But trust me, this is far from a purely academic exercise, a bit of intellectual gymnastics with no real-world consequences. This very question has shaped the entire course of Western science. It has fueled some of the most important debates in our cultural history, influencing how we understand the universe, how we develop technologies, and even how we think about our place within the cosmos. Our story begins long before the days of spaceships and smartphones, long before even Galileo and Newton were gazing at the stars and pondering the laws of motion. It's a story that stretches back centuries to the very beginnings of modern science, and it's a story that's still being written today in laboratories and universities around the world. So, are you ready to jump in and explore this fascinating intellectual landscape? Are you ready to grapple with these fundamental questions about science and its relationship to reality? Let's embark on this journey together and see where it takes us. Okay, let's dive even deeper into this cosmic tale and flesh it out further, ensuring we capture the richness of the original blurb while keeping it conversational and engaging. Let's turn this into a proper philosophical adventure, filled with quirky asides, thought-provoking questions, and a dash of humor. All right, picture this: you're standing under a vast, star-studded sky. It's a clear night, and the Milky Way is splashed across the heavens like a cosmic artist's brushstroke. Have you ever felt that sense of awe, that humbling feeling of being a tiny speck in a universe far grander than you can comprehend? Well, our ancestors felt it too, and it sparked something incredible: the birth of astronomy, one of the most ancient scientific disciplines known to humankind. But this isn't just a course about stars and planets. It's a journey into the very heart of how we think, how we know, and how we grapple with the nature of reality itself. It's about the evolution of human thought, wrapped in a celestial package. From the ancient Mayans to the Babylonians, civilizations across the globe were obsessed with the celestial dance above. They weren't just casually stargazing, mind you. They meticulously tracked the movements of stars and planets, building intricate observatories and developing complex calendars. They even crafted stunning instruments like astrolabes. Imagine beautifully engraved brass devices that acted as ancient GPS systems for the sky, allowing them to navigate and tell time by the stars. These weren't just tools, they were symbols of humanity's burning desire to understand our place in the cosmos. And the Japanese even created planispheres based on Korean maps of the sky. Just stop for a moment and imagine the dedication of these people. Now, let's teleport to ancient Greece, where the plot thickens. We meet Ptolemy, a true celebrity astronomer of the 7th century AD. He envisioned the universe as an elegant, geocentric system, Earth at the center with everything else revolving around it in perfect circular orbits or orbital shells. It was a beautiful, tidy model like a cosmic clockwork designed by a master craftsman. But, as with any good story, there's a twist. Sometimes, those pesky planets seem to throw a wrench in the works by performing a little backward jig in their trajectories, a phenomenon we now call retrograde motion. It's as if the planets decided to moonwalk for a bit, just to keep things interesting. This was already well known by the Greeks, who struggled for a long time to explain it. To explain this celestial hiccup, Ptolemy came up with the ingenious, yet somewhat convoluted, idea of epicycles. Picture this planet just moving in large circles around the Earth. They were also doing mini-loop, D-loops long smaller circles attached to the larger ones. It's like a cosmic waltz with a few extra twirls thrown in. But here's the really fascinating part. Ptolemy and his fellow astronomers weren't necessarily claiming that this was the literal truth of how planets moved. They were more like, okay, this model is a bit complex and maybe a tad wacky, but it works. It allows us to predict where the planets will be, and that's what matters. Even they did not consider this to be the truth about planetary motion. This idea that the ancient astronomers were more concerned with creating a working model than with uncovering ultimate reality is where the French philosopher Pierre Duhem enters our story. In his brilliant book, To Save the Phenomena, Duhem beautifully captures this concept, arguing that the goal of ancient astronomy was to save the appearances, to create a system that matched observations, even if it didn't perfectly reflect the underlying reality. It's like saying, hey, as long as the math works out, we're good. This raises a fundamental question. Is the goal of science to uncover absolute truth, or is it enough to create models that accurately describe and predict what we observe? Where do we even draw the line? Then, in 1543, the plot takes a dramatic turn with the arrival of Nicolaus Copernicus. This is where things get revolutionary, quite literally. Copernicus publishes De Revolutionibus Orbium Coelestium, so which translates to On the Revolutions of the Celestial Spheres, a book that dares to suggest a radical idea. What if, just maybe, the Earth isn't the center of the universe? What if it actually revolves around the Sun, along with the other planets? He presented his argument very carefully by stating that he was just experimenting, like his predecessors, with fictive circles to save the celestial phenomena. He knew his views were absurd, and yet, he states that his heliocentric hypothesis was more certain than any of the fictitious hypotheses of his predecessors. Copernicus presents his heliocentric model almost apologetically, acknowledging the long-held tradition of astronomers being granted the freedom to invent fictive circles to explain celestial phenomena. He even writes a letter to the Pope, humbly suggesting that his model is just another attempt to save the appearances, albeit a more promising one. It's as if he's saying, hey, I know this sounds crazy, but hear me out. Even though he was cautious, Copernicus subtly hints that his model might be more than just a mathematical trick. It might actually reflect the true structure of the cosmos. Copernicus died the same year his book was published. Perhaps luckily, as the book was published with an anonymous preface that mitigated the spirit of his work by representing it as just another exercise in the tradition of saving the phenomena. It stated that it is not necessary that these hypotheses be true, nor that they be likely, but they just allow for calculations to be made. But the real fireworks don't start until nearly half a century later, thanks to the one and only Galileo Galilei. This is where our story takes a truly rebellious turn. Galileo, a bold and brilliant astronomer, wasn't content with merely saving the phenomena. He examined Copernicus' work and using his trusty telescope, he gathered evidence supporting the heliocentric model. But he didn't stop there. Galileo did something incredibly daring for his time. He claimed that the Copernican system wasn't just a useful model. It was a true description of the heavens. This bold claim challenged not only the prevailing scientific views, but also the powerful religious authorities who held a geocentric worldview as dogma. Galileo's insistence on a sun-centered universe was seen as heresy, and he found himself in a serious conflict with the Church. This clash between science and religion, sparked by Galileo's unwavering pursuit of truth, is a pivotal moment in our story. It highlights the tension between intellectual curiosity and societal norms, between the desire to understand the universe and the fear of challenging established beliefs. How do we balance these things? Is it worth rocking the boat if you think you are right? This whole saga, from the ancient stargazers to the revolutionary ideas of Copernicus and Galileo, is more than just a history of astronomy. It's a captivating exploration of how our understanding of the universe and our place within it has evolved over millennia. It's a story about the power of observation, the beauty of mathematical models, and the courage to challenge the status quo. So, are you ready to embark on this intellectual adventure? This course is an invitation to explore the cosmos not just as astronomers, but as philosophers, as storytellers, and as curious minds. We'll delve into fundamental questions about the nature of knowledge, the limits of human understanding, and the relationship between science and belief. We'll laugh at the quirks of history, marvel at the ingenuity of ancient thinkers, and ponder the profound implications of our ever-evolving understanding of the universe. Let's uncover the fascinating history of how we've come to know, or at least try to know, the cosmos, one star, one episcopal, and one revolutionary idea at a time. All right, let's dive deeper into this cosmic tale of curiosity, telescopes, and a universe that refused to stay put. We're going on a journey, not just through space, but through the evolution of human thought, sparked by a man who dared to question the heavens. Picture this: Venice, 1609. It's a time when your smartphone was just a twinkle in a sci-fi writer's eyes, if there had been any sci-fi writers, that is. But even without Google Maps, news traveled, and word reached a certain Galileo Galilei, a man with a mind as restless as the tides about a nifty invention making waves in the Netherlands. This wasn't your average party trick. It was a spyglass that could incredibly make distant objects appear closer. Think of it as the Renaissance version of a zoom lens, only way cooler because it was brand new and nobody really knew what to do with it yet. Now, Galileo, being the kind of guy who probably took apart clocks just to see how they worked, decided to build his own. At first, he used his telescope for practical stuff, like identifying ships as they approached the bustling Venetian port. This was a neat trick, no doubt, kind of like using a supercomputer to check your email, functional, but hardly tapping into its full potential. But Galileo's gaze wasn't confined to earthly affairs. His curiosity was a cosmic itch that needed scratching. A few months later, he crafted a more powerful telescope, one that could magnify objects 30 times. Imagine the sheer awe when he pointed this bad boy at the moon. What he saw was about to shatter centuries of accepted wisdom. Instead of the smooth, perfect sphere everyone had imagined, the moon was revealed to be a rugged, textured world, full of mountains and craters. Galileo, who was also a gifted writer, captured these lunar landscapes in beautiful detail in his 1610 publication, The Starry Messenger. It became an instant hit, the 17th century equivalent of going viral, because it didn't just describe the moon. It challenged the very fabric of the cosmos as people knew it. This wasn't just about seeing the moon close up, it is about the shift of the perception of our place in the cosmos. See, for ages, the teachings of Aristotle and Ptolemy had painted the heavens as a realm of perfection, completely different from our messy, imperfect Earth. They envisioned a universe where celestial bodies were flawless, unchanging, and moved in perfect circles. Galileo's moon, with its decidedly imperfect features, was like a cosmic graffiti artist tagging over a pristine wall. It was a visual nope-nope to the old way of thinking. But Galileo was just warming up. The universe had more surprises in store, and he was ready to uncover them. In January 1610, he observed what he initially thought were 4 stars wandering around Jupiter. These, it turned out, were Jupiter's moons, doing their own celestial dance. It was like discovering a mini solar system within our own, a mind-boggling revelation at the time. Then in December, he noticed that Venus went through phases, just like our moon. This was the clincher. The Ptolemaic system, which placed Earth firmly at the center of everything, simply couldn't explain these observations. It was like trying to fit a square peg into a round hole. The cosmic math just didn't add up. Suddenly, Copernicus, who had been ridiculed for suggesting a sun-centered universe, started looking like a genius. Galileo, armed with his telescopic evidence, didn't just see Copernicanism as a neat hypothesis, he embraced it as a physical truth. He believed that this new, sun-centered model was the way the universe actually worked. And in a move that was both bold and controversial, he argued that this scientific truth could coexist with religious faith. He penned a letter to the Grand Duchess Christina, making his case for a universe where science and religion could hold hands and skip through the cosmos together, a radical concept at the time. Unsurprisingly, the Catholic Church, which had long championed the Earth-centric view, wasn't thrilled with Galileo's cosmic revelations. What followed was the Galileo affair, a historical showdown that's still debated today. It's a story of power, faith, and the clash between old and new ideas. But here's the philosophical gold we're mining. Galileo wasn't just an astronomer, he was a revolutionary thinker who changed how we approach the universe. He argued that science shouldn't just be about saving the phenomena, creating models that fit observations, no matter how convoluted. Instead, he believed science should aim to uncover the true story of the universe. He was asking the fundamental question, what is really out there and how does it actually work? Rather than, what explanation can we come up with to maintain our current beliefs? This shift in perspective was like opening Pandora's box, but in a good way. Once the idea took hold that the universe might be vastly different from what we thought, there was no going back. The universe, once imagined as a small enclosed sphere, was about to be revealed as an infinite expanse, full of wonders beyond our wildest dreams. So join us as we trace the profound impact of Galileo's ideas from his time to ours. We'll explore how his way of thinking, his insistence on seeking the true story of the universe, continues to shape science today. We'll delve into the philosophical implications of a universe that's constantly surprising us, and how our understanding of our place in the cosmos has evolved from a cozy, Earth-centered bubble to the vast, awe-inspiring reality we're still exploring today. It's a journey of discovery, and we're all invited to come along for the ride. And who knows what other cosmic graffiti we might find along the way. Alright, buckle up, because we're about to dive deep into the rabbit hole of scientific philosophy. Ever stop to think about what science is actually trying to achieve? Is it just about building cool gadgets and making accurate predictions, like some kind of super-powered, ultra-precise, futuristic weather forecast on steroids? Or is there something more profound going on, a grand quest to decipher the fundamental truths of this mind-bogglingly complex universe we find ourselves living in? Let's rewind a bit and consider Galileo, a true rock star of science. This guy wasn't satisfied with just drawing pretty pictures of the stars and planets and calling it a day. No way. He was convinced that science should be giving us the real, unadulterated truth about the cosmos, not just some half-baked model that sort of fits the observations if you squint hard enough. This bold perspective has a fancy name in the world of philosophy: scientific realism. It sounds intimidating, but trust me, the core idea is pretty intuitive. Scientific realism is like saying, scientists are talking about things like planets or electrons or gravitational waves. They're not just playing a game of make-believe with cool-sounding jargon. They genuinely believe they're describing real entities that exist out there in the vast expanse of the universe. We can break this down into two juicy parts. First, there's the language aspect. It's like, when a scientific theory mentions planets, it's not just using a convenient label, it's talking about those massive, usually spherical, celestial bodies that are doing their own dance around a star. Same deal with collectrons, or quarks. They're not just abstract theoretical figments of the imagination, but actual, tiny particles with specific properties engaging in a subatomic ballet. This may sound like stating the obvious, but trust me, it's a philosophical can of worms that's been debated for centuries. Secondly, we have the belief part, or the epistemic aspect, as the philosophers like to call it. When scientists accept a theory, after rigorous testing and debate, they're not merely saying, well, this seems to be a handy tool for making predictions, might as well use it. They're planting their flag and declaring, we genuinely believe this theory is a true, or at least a very close approximation to a true, description of how reality operates. In other words, the statements the theory makes about those planets or electrons or whatever actually correspond to real-world facts, to the way things are arranged and behave in the universe. Now, you might be thinking, isn't that just common sense? But hold your horses. For a surprisingly long time, many brilliant minds like Ptolemy, Simplicius and Osiander back in the day had a very different take on science. They were more in the who cares if it's actually true as long as it works camp. They were happy with models that could predict the movements of celestial bodies, even if those models didn't necessarily reflect the underlying reality. So, to justify this whole scientific realism thing, we need a truly compelling argument. And that's where the wonderfully, almost comically named, no miracles argument struts onto the stage. Imagine Hillary Putnam, a philosophical heavyweight, throwing down the gauntlet and saying, "All right, folks, let's be real for a second. If scientific realism isn't true, if our best scientific theories aren't at least approximately true descriptions of reality, then the astonishing, mind-boggling success of science is nothing short of a series of incredibly lucky coincidences, a freaking miracle." Think about it. If the stuff our theories talk about, like curved space-time, or the strong nuclear force, or electromagnetic fields, doesn't actually exist in some form, how on earth can we explain the fact that these theories are so incredibly good at predicting how things will behave? Consider the grand narrative of scientific progress. We don't just jump from one theory to another willy-nilly. We replace old, less accurate theories with new, refined ones that do a better job of explaining the world. Like Newtonian mechanics, with its elegant equations of gravity and motion, was a monumental achievement. But then along came Einstein with his theory of relativity, which provided an even more accurate picture, especially when dealing with very strong gravitational fields or speeds approaching the speed of light. The no miracles argument posits that this progression isn't just a random walk. It happens because we're gradually zeroing in on the truth, getting closer and closer to understanding the same underlying things that make up the universe. If those things, like the curvature of spacetime predicted by Einstein's theory, weren't actually real features of the universe, then the uncanny accuracy of these theories in explaining phenomena, like the slightly eccentric orbit of Mercury or the bending of starlight around massive objects, would be, to put it mildly, utterly miraculous. It would be like flipping a coin and getting heads 1,000 times in a row. Possible. Sure. But highly improbable, right? So, the no miracles argument is essentially a grand detective story. It says that the only plausible, non-miraculous explanation for the astonishing track record of science over centuries is that our best theories are, at least approximately, on the right track. They're not just convenient fictions or useful tools, they're genuine glimpses into the intricate, awe-inspiring machinery of reality. And that, my friends, is a thought worth savoring, a mystery worth exploring, and a testament to the power of human curiosity to unlock the secrets of this amazing universe we inhabit. It makes you wonder what incredible discoveries are just around the corner, waiting to be unveiled by the next generation of scientific sleuths. All right, let's dive deeper into this philosophical rabbit hole and explore the fascinating world of how we understand science with a bit more detail, shall we? It's a bit like peeling back the layers of an onion, except instead of tears, we might find some mind-bending insights. So, picture this: we're all detectives in the grand mystery of the universe, trying to figure out what's really going on. Some folks, the scientific realists, are like the super confident detectives who are absolutely convinced they've cracked the case. They believe that science isn't just a good guess, it's the ultimate truth. They're the ones who say that when science talks about things like tiny electrons or distant galaxies, it's describing reality exactly as it is, even the stuff we can't see with our own eyes. They believe in the literal truth of scientific theories, like a gospel. But hold your horses. There's another group of thinkers, a bit more cautious, a bit more like the detectives who always double-check their evidence. We'll call them the constructive empiricists. And they're the stars of our show today. They're not saying science is wrong, not at all. They just think we need to be a bit more nuanced about what it means for a scientific theory to be true. One of their leading lights is a philosopher named Bas van Freysen. He and his crew agree that when scientists talk about electrons or planets, they're referring to real things out there in the universe. No disagreement there. But, and here's the twist, they question whether we need to believe our scientific theories are perfectly 100% true in order to appreciate their value and usefulness. They are asking, can a theory be incredibly useful and explanatory without being a literal mirror of reality? Now, constructive empiricism might sound like a fancy, jargon-filled term, but it's actually a pretty cool and surprisingly relatable idea. It's like saying, scientists are a bit like master builders constructing intricate models to explain the phenomena they observe. Think of it like building with Legos. You can create a magnificent, detailed model of a castle, complete with towers, a drawbridge, maybe even a dragon. But that doesn't mean there's a real tiny kingdom with miniature knights and princesses living inside your Lego creation. Similarly, scientists build models, not with plastic bricks, but with concepts, equations, and experiments to represent how the world works. These models are incredibly useful tools. They help us make predictions, understand complex processes, and even develop new technologies. But the constructive empiricists, like our cautious detectives, remind us that these models might not be exact to scale replicas of reality. And the empiricism, part of the name, that just emphasizes their focus on what we can observe and test through experiments. They believe that knowledge should be grounded in empirical evidence, in what we can actually experience. Let's take minerals as an example to illustrate this point. We can observe and measure all sorts of things about minerals, right? We can determine their melting points, see how hard they are, observe how they react with other substances. But what about their atomic structure, the very building blocks that make them up? We can't exactly whip out a super-powered microscope and count the individual protons and neutrons in a gold atom, can we? That's where the realm of the unobservable comes in. Chemists tell us that gold has an atomic number of 79, which means it has 79 protons in its nucleus. That's incredibly useful information for understanding gold's properties and how it interacts with other elements. But can we directly observe those 79 protons? Nope. So what do? We build models. Think of those cool crystal structure diagrams you might have seen with different colored balls representing different atoms, all connected by lines representing chemical bonds. They are beautiful and instructive. These models help us visualize and understand how atoms are arranged within a mineral. They can even help us predict how a mineral might cleave or fracture based on the strength of those bonds. But our constructive empiricist friends would point out, these models are more like helpful metaphors or analogies than perfect, literal pictures of the atomic world. They are tools that help us grasp abstract concepts, make calculations, and make sense of experimental results. So, a good scientific theory, according to constructive empiricists, doesn't necessarily need to be literally true in every detail to be incredibly valuable. It needs to be empirically adequate. That means it has to accurately describe and predict the observable phenomena, the things we can actually see and measure, whether they happened in the past, are happening now, or will happen in the future. It's like a good detective story. It has to fit all the known facts and clues, even if it might not capture every single detail of the crime scene perfectly. Now, this idea of saving the phenomena isn't entirely new. If we jump in our time machine and travel back to ancient Greece, we'd find that astronomers back then also thought the goal of their work was to explain what they observed in the heavens. But their reasons were a bit different. They believed that ultimate truth was reserved for the gods, and mere mortals couldn't access it. After Galileo came along and shook things up, that view became a bit outdated. But modern anti-realists, like our constructive empiricists, have other, more nuanced reasons for being cautious about claiming absolute truth for scientific theories. One reason is that scientific models are often simplified and idealized. They're like sketches rather than high-resolution photographs. Think about those iconic DNA models, the double helix. They're incredibly helpful for understanding the basic structure of DNA, but they leave out a lot of the messy, complex details of a real cell's environment. It's like drawing a stick figure to represent a person. It conveys the basic idea, but it's not exactly a realistic portrait, is it? Similarly, scientific models often abstract away from certain complexities to focus on the most important aspects of a phenomenon. Another reason for their caution is a bit like a philosophical what if? What if the things we currently believe to be true based on our best scientific theories turn out to be wrong in the future? History is full of examples of scientific ideas that were once widely accepted but were later overturned. Remember, phlogiston, the substance once thought to be responsible for combustion, or caloric, the fluid once believed to carry heat. These were once considered fundamental elements of the universe, but now they're just footnotes in the history of science. So, maybe it's a bit hubristic, a bit too bold, to claim that our current scientific theories have finally grasped the ultimate, unchangeable truth. Maybe it's more intellectually honest, more humble to say, this is the best understanding we have right now, based on the available evidence, and it works incredibly well for explaining and predicting what we observe. That, in a nutshell, is the spirit of constructive empiricism. It's a perspective that combines a deep appreciation for the power and achievements of science with a healthy dose of intellectual humility. It's a reminder that the pursuit of knowledge is an ongoing journey, a process of continuous refinement and revision, rather than a destination where we finally plant a flag and declare, "We've figured it all out." It's a philosophy that encourages us to be curious, to be skeptical, and to always be open to the possibility that our understanding of the universe, like the universe itself, is constantly evolving. They are not against progress or science, but they believe that attaching metaphysical belief to a theory is not necessary for the theory to be good and useful. Okay, let's dive into the fascinating, and sometimes mind-bending, world of scientific realism. Buckle up, because this is where philosophy meets the cutting edge of science, and things get interesting. Imagine you're a detective, but instead of solving a crime, you're trying to figure out the nature of reality itself. You've got clues, but they're not always straightforward. You have these wildly successful scientific theories that seem to explain everything from the smallest particles to the vastness of the cosmos. But here's the kicker. These theories talk about things we can't directly see, like electrons, quarks, or the curvature of space-time. So, the big question is, should we believe these theories are literally true, that these unseen entities are just as real as the chair you're sitting on? This is where scientific realism comes in, boldly claiming, "Wes, these theories are our best window into reality, and those unseen things are real." But wait, there's a twist. Enter constructive empiricism, a more cautious approach championed by philosopher Bas van Fraassen. It's like saying, hold on, maybe we don't need to go that far. Our theories are incredibly useful tools, like super-powered magnifying glasses that help us predict and understand what we can observe. But whether those unseen things are actually real, maybe that's a question we can't, and don't need to, answer. This is based on their idea of empirical adequacy, which suggests that a good theory is one that correctly predicts what we can observe, not one that has a bearing on some unobservable reality. Now, the realists aren't going to take this lying down. They have some powerful comebacks. Their first shot is something called the no miracles argument. It basically goes like this. Look, our scientific theories are ridiculously successful. They make incredibly accurate predictions, and they've led to amazing technological advancements. It would be a miracle if these theories were so successful without being at least approximately true. They argue that the success of a theory is what should guide us, suggesting that successful theories are true because of the reality and approximate truth of the entities they postulate. Conversely, it suggests that failed theories, e.g. phlogiston theory, are not true, and their lack of success can be attributed to their falsity. The second realist rejoinder takes aim at the very idea of separating the observable from the unobservable. They ask, why should we trust our naked eyes more than our super-sophisticated scientific instruments? Isn't an electron microscope just as valid a way of seeing as our own eyes? Think about it, we've never seen a dinosaur with our naked eyes, but we believe they existed based on fossil evidence. Is that so different from believing in electrons based on the evidence from a particle collider? Philosophers like Philip Kitcher and the late, great Peter Lipton argued that the way we reason about unobserved observables like dinosaurs is the same way we reason about unobservables like electrons. We use something called inference to the best explanation. IBE. It's like being a scientific Sherlock Holmes. We gather evidence, consider different hypotheses, and then choose the one that best explains the evidence. For example, we infer that dinosaurs existed because that's the best explanation for the fossil record. Similarly, we infer that electrons exist because that's the best explanation for the data coming out of experiments. IBE is a powerful tool, not just in science but in everyday life. When your doctor diagnoses you based on your symptoms, they're using IBE. When astronomers conclude the universe is expanding based on the redshift of starlight, they're using IBE. So, where does this leave us? The debate between realists and constructive empiricists is far from over. It's a lively ongoing discussion that touches on fundamental questions about the nature of science, knowledge, and reality. It's a reminder that science isn't just about collecting facts, it's also about interpreting them, and that interpretation can be a surprisingly complex and fascinating process. It seems, the realists say, that what science is all about is inferring the best hypothesis out of a collection of competing ones, and that we do not necessarily need to see something to believe it is real. Instead, our belief in the unobservable entities of our universe should come from the validity and robustness of our inferential practices. And who knows, maybe one day we'll have a definitive answer. Or maybe, just maybe, the journey of asking these questions is more important than the destination. What do you think? Is the universe really made of these unseen things our theories describe, or are they just useful fictions? Let the philosophical pondering begin. All right, folks, buckle up because we're about to dive into one of the most mind-bending debates in the philosophy of sciences, the epic showdown between realism and anti-realism. It's a bit like a philosophical Avengers Endgame, but instead of superheroes, we have ideas battling it out for the fate of, well, scientific truth. On one side, we've got the scientific realists, the champions of truth. Imagine them as the Indiana Joneses of philosophy, convinced that science is on a grand quest to uncover the real, hidden treasures of the universe. They believe that our best scientific theories, especially the ones that have stood the test of time, aren't just convenient stories, they're actually true, or at least pretty darn close to the truth. They're like, hey, if these theories weren't true, if the tiny invisible stuff they talk about, like atoms and quarks, didn't actually exist, then how on earth do we explain the mind-blowing success of science? It would be a total miracle, a cosmic coincidence of epic proportions. This is what they call the no miracles argument, a pretty convincing point, right? But wait, here come the anti-realists, the cool, collected skeptics of the bunch, led by their philosophical guru, Bas van Frassen. They're like the wise Yodas of the debate, urging us to chill out a bit about truth. Van Frassen, with his constructive empiricism, says, hold on a minute, folks. Science doesn't need to be true to be good. Science is doing fine just aiming for theories that fit the observable facts. Theories that are empirically adequate. Think of it like building a really good map. The map doesn't have to be a perfect atom-for-atom replica of the territory to be incredibly useful. It just needs to accurately represent the parts we can see and interact with. In his view, models that are adequate to the phenomena are more than enough, and there is no need to commit to the existence of things we cannot observe. So, how do the realists strike back? They bring in their secret weapon, inference, to the best explanation. It's like being a detective at a crime scene. You see clues, you consider different explanations, and you go with the one that makes the most sense, even if it involves things you didn't directly witness. Realists argue that we should do the same with science. If the best explanation for why our theories work so well is that they're true, even about the invisible stuff, then we should believe in those invisible things: atoms, electrons, DNA, the whole shebang. It is pretty much the same as believing in dinosaurs, even though we only know them by their traces like fossils. Now, where does this intellectual roller coaster leave us? Well, just like any good philosophical saga, the debate rages on. Over the past few decades, a whole bunch of new philosophical positions have popped up, each trying to be the peacemaker in this epic battle. It's like a never-ending game of philosophical rock, paper, scissors, with new players constantly joining the fray. As our scientific understanding expands and evolves, so do our ideas about what science is and what it can tell us about the universe. But that's a story for another time, a sequel, if you will. For now, let's just marvel at the fact that we humans, with our curious minds, can even have these kinds of mind-blowing debates. It's a testament to the power of philosophy and the endless quest for understanding. And who knows, maybe one day we'll finally crack the code of reality. Or maybe we'll just keep enjoying the ride, forever pondering the mysteries of the universe.